Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on August 19, 2025, which was just 2 days ago. The standout result is that a self-play approach with variational problem synthesis lifts pass at 32 dramatically, with absolute gains of 18.3% on AIME24 and 22.8% on AIME25, while keeping generation diversity intact. The paper is titled Beyond Pass at 1. Self-play with variational problem synthesis sustains RL versus R, and the implications for model training are quite significant. In short, the method sustains policy entropy, boosts pass at K broadly, and works across models from 3 billion to 32 billion parameters. Building on that momentum, the visible post highlights self-verification via dual preference optimization, noting relaxed cycle consistency as a clever training trick that could generalize broadly. Engagement looks solid with around 80 likes. Alright, we are looking at a two-panel figure that tracks AIME accuracy over training steps, comparing S versus S in red with standard RLVR in blue. The left panel shows pass at 32, where red points and the trendline keep rising past 450 steps, while blue plateaus and then dips. The right panel shows pass at 1, which also climbs steadily for S versus S but flattens for RL versus R. Together, these trajectories indicate sustained gains, because the self-play synthesis keeps exploration active. Next, we are looking at a two-panel graphic that tracks training dynamics with and without augmented problems. The left panel shows policy entropy over steps, where the blue baseline steadily falls, while the red augmented line declines slowly, then rebounds after the data update, which signals renewed exploration. The right panel plots pass at 32 on competition benchmarks, and the red curve rises notably after the same update, whereas the blue curve plateaus. Together, these panels show that online augmentation sustains diversity and converts it into accuracy gains. Now we are looking at the full workflow diagram, which maps one training iteration from batch sampling to the policy update. The left block shows original problem solving, where the model answers sampled problems and keeps the challenging subset because their group accuracy sits in a middle band. The center block illustrates variational problem synthesis and then synthetic problem solving, which reuse correct solutions to create new statements that share the same answer. The right block shows filtering rules that decide what enters the experience buffer, so only informative items drive the update. Now we are looking at Table 1, which compares pass at 1 and pass at 32 across several math benchmarks for different training regimes. You can see two blocks by training data, Math 12K and DAPO 17K, and within each block, S versus S consistently beats standard RL versus R. The biggest jumps appear in pass at 32 on AIME24 and AIME25, where gains reach double digits. These results reinforce that online synthesis sustains exploration and converts it into higher pass at K. Moving to the results, we are looking at a four-panel figure that scales pass at K from 1 up to 1024 across AIME24, AIME25, Beyond AIME, and Math 500. You can see three curves per panel, where S versus S consistently sits above both the initialization and RLVR baselines. The gaps widen at larger K, which signals broader reasoning coverage as sampling increases. On Math 500, the advantage persists even at very high K, so exploration translates into steady gains rather than saturating early. Wrapping up, two takeaways stand out. First, self-play with variational problem synthesis keeps policy entropy from collapsing, so exploration stays alive and pass at K rises. Second, gains are strongest at larger K, signaling broader reasoning coverage. Reinforcement learning with verifiable rewards means rewards come from auto-checkable answers. I am Alex. Thanks for listening to the AI Research Roundup.